Welcome everyone to the second part of reviewing Unit 5 past paper problems. If you find this content enjoyable or you want to see more, don't forget to subscribe. Okay, without further ado, let's get into the questions. A man sits on a buggy that is pulled along by a wire attached to a kite. The wire is at an angle of 40 degrees to the horizontal and has a constant tension of 200 newtons. The man in the buggy traveled a distance of 20 meters along a straight horizontal path. The wire and the path of the buggy are in the same vertical plane. What is the work done by the tension on the man in the buggy? So you should know this formula of work. We know that work is the product of force times distance, displacement, denoted by the letter S. In this case, we are given both the force and the distance. So we can simply just multiply these two. So 200 newtons multiplied by 20 meters is equal to work. And it turns out if you multiply this out, you get around 4.0 kg. That's the answer, right? This isn't the total answer because as shown in the diagram, the tension of the wire is going at an angle upwards. As a result, this force is not entirely 200 newtons because some force is being wasted going vertically and some force is going horizontally. So we need to find the horizontal component of this 200 newtons. To do so, we can use the angle given to us. So work is equal to 200 newtons multiplied by the cosine of 40 degrees, and that's our force, multiplied by the distance, which is 20 meters. And if you plug that into your calculator, 200 times cosine 40 times 20, you get about 364 joules. In this case, to 2 civics, it's going to be B. Okay, so a projectile for number 11. Okay, for number 11, a projectile of mass 0.25 kg is at a height of 30 meters above horizontal ground and traveling at a speed of 15 meters per second. A short time later, it is at a height of 35 meters above the horizontal ground and is traveling at a speed of 5.0 s-1. How much work is done against air resistance during this time? So we know that this work is equal to force times distance. It is in the same units as energy, right? It's in joules. That's the unit. So for this particular problem, you solve this using the conservation of energy. In this case, the kinetic energy plus the potential energy before something happens and after something happens is the same. So in this case, our energy initial is equal to the E of KE, the kinetic energy initial, plus the potential energy initially. So we can substitute using the equation. 1/2 mv squared, where m is given here, 0.25, and a speed of 15 meters per second squared. Our potential energy is denoted by the equation of mg and the change of h. I should write in these equations so it's a little bit more clear. Right, so we do this. Multiply the change in y, and our change in y is given here by the height of 30 meters. And this is going to be equal to our EF, where E of F is equal to the kinetic energy final and the potential energy final. So in this case, we have 1/2 mp squared m doesn't change, so it's 0.25. Our v is going to be 5 here, 5 squared, plus m, so 0.25, multiplied by 9.81, multiplied by 35 here. And you just have to use your calculator to calculate this out real quick. So for initial, it's going to be 101.7 joules. And for the final, it's going to be about 88.962. And then if we subtract these two, you get that it's about 13 joules. And then our answer is B. Define power. So this is question number 12. So the first AI is going to be power definition. So we can say that our power definition is work divided by time. Mechanical power P can be calculated using the formula P equals FV. Use the concept of work and the definition of power to show how this formula is derived. So work is equal to F times S, right? And then P is equal to work divided by time. So in this case, we can say that P is equal to F times S over T. And then you can actually separate this into F multiplied by S over T. And then it turns out this is equal to V. So then we get our final equation of F of V. Which is to be shown. The engine of a lorry provides 130 kilowatts of power to a lorry's wheels when it is traveling at a constant speed of 25 meters per second along a straight horizontal road. Show that the resistive force opposing the motion of the lorry is 5,200 newtons. So, as we said before, P is equal to force times velocity. So our velocity in this case is 25 meters per second as given, multiplied by F, which is what we're showing, and then 130 kilowatts. So all we need to do is move this 25 meters per second to the other side, and then we get F. So then F is equal to 130k watts over 25 meters per second. If you divide this, you will get 5,200 newtons. One thing I kind of did through the calculator is that this kilowatts is expanded out, okay? Because in power, the units are watts, newtons, and meters per second. So when they give you as a unit of kilowatts, you have to convert it into watts, which is multiplying by 1,000, basically. If somebody says 100k, you know it's going to be 100,000, right? Similarly here, so it's going to be like 130,000 watts over 25 meters per second. And then you will get the same answer as here. Okay, for C, the lorry in B travels up a straight section of the road that is inclined at an angle theta to the horizontal as shown in F figure 3.1. The lorry has mass m and acceleration of free fall is g. Determine an expression in terms of fg, mg, and theta for the component of the weight of the lorry that acts parallel to the surface of the road. So we're looking at it for an angle. So if we have an object, in this case it's going to be the truck, right? It's going to be at an angle. I'm going to make it the angle a little bit large so that the difference is actually seeable, right? So this is going to be mg, right? And then these two are angles. So it turns out that this force here is mg, and then we're looking for it parallel to the surface of the road. So since this is perpendicular and this is also perpendicular, we can see that we're looking for this component right here. As a result, since we know that this is angle theta, we can say that the parallel is just going to be mg sine theta. The total resistive force remains unchanged at 5200 newtons, and the engine now provides greater power to maintain the speed of 25 meters per second. The total mass of the lorry is 36,000 kg. The angle is 1.4 degrees. Determine the power in kilowatts now provided by the engine. So first, you know that F is equal to, no, sorry, not F, P. P is equal to F times velocity. And we have to figure out the force of the engine that goes up, right? So F, in this case, is going to be the resistive force plus F of G, which we'll calculate, right? So we already solved for F resist, and they still give it to us in the problem. So in this case, this is going to be 5,200 newtons. Then F of G is simply going to be 36,000. We're using this formula down here, by the way. Multiplied by 9.81, multiplied by sine of 1.4 degrees. And then hurry up and calculate that. And then you get that the total resistive force is going to be about that much. So then P is going to be equal to 13828.5 newtons multiplied by the speed, which is going to be 25 meters per second. And this is about 2.8 kilowatts. A car of weight 15,000 newtons is traveling along a horizontal road. At one instance, the thrust force acting on the car from the engine is 12,000 newtons, and the resistance force acting on the car is 3,000 newtons. The velocity of the car at this instant is 24 meters per second. What is the power outage from the engine? So power is going to be equal to force multiplied by the velocity, right? Just trying to make sure that they give us resistive force and the weight of the car, whether or not that information is actually important and factors into the actual question, right? So I think this is the main idea that we're using. Yes. Okay. So they're asking for the power output from the engine specifically, which is producing the thrust force. So it's going to be 12,000 multiplied by 24 meters per second is equal to P. And if you multiply this out, Okay, so number 14, a student attempts to derive the formula for kinetic energy E of k. She begins by considering an object of mass m which is initially at rest. A constant force F is applied to the object, causes it to accelerate to final velocity v and displacement s. The kinetic energy gained by the object is equal to the work done on the object by the force F. Which equation would the student not need in order to derive the formula for E of k? So we have these various formulas to account for, right? So we're given that kinetic energy is gained by the force is equal to the work done and the object of F. So we actually do need these definitions of A and B because they both define kinetic energy. So there's no way it can be A and B. Moreover, it says that a constant force F is applied to object, which causes it to accelerate to a final velocity v and displacement s, right? So when we need to solve it, we actually need to use this kinematic equation. So this is not the answer. Thus, by elimination, our final answer is C. For number 15, a stone is falling vertically through the air at a constant terminal velocity. Which energy change is occurring? So if a stone is falling vertically through an air, we know that the gravitational energy is going down and is being converted to kinetic energy of the stone due to the conservation of energy. If you don't know what this is, you should try and restudy this definition. Sorry for the bad handwriting. But this case, if you quickly scan the answers, this is the only one that goes from potential energy to kinetic energy. It is possible that gravitational potential energy is converting into thermal energy, but that is more like friction with air molecules. It's just not very like significant in this case, so it's negligible, I think. Thus, it's not going to be A. And the stone is not going up, and thus the kinetic energy is not being converted into gravitational potential energy, but the other way around. And D is the same thing as what I said about A. Okay, number 16. A lamp is switched on for 2.0 hours. The power input to the lamp is 1.0 watts. The energy given out by the lamp as light is 7.0 times 10 to the third joules. How much energy is converted to other forms by the lamp? Okay, so we know that power is equal to work over time. In this case, our power is 1.0 and our time is 2.0 hours. And then 2.0 hours, if you convert this, you have to convert this into seconds because the basic unit, SI units for power is in seconds. So this is going to be 3,000. So in this case, it's going to be around 360 watts is equal to the amount of work. Which in this case, sorry, this is not watts, this is joules, and where this is the total amount of work by the input. And thus, we know that our total amount of energy is 7.0 times 10 to the third joules. So we can simply do 7,000 minus 360, which then becomes 340 joules. So it's going to be C. Okay, for 16, a lamp is switched on for 2.0 hours. The power input to the lamp is 1.0 watts. The energy given out by the lamp as light is 7.0 times 10 to the third joules. How much energy is converted by other forms by the lamp? So we know that power is equal to work divided by time. In this case, our power output is 1.0 watts. Our work is to be determined, our total amount of work. And then our time is 2.0 hours. And we have to convert this into seconds because the base SI units for power is in seconds. So if we convert this, we have to multiply this out, and then we get that work is equal to 7,200 joules. So this is the amount of total work, I should say. It says that the energy given out by the lamp as light is 7.0 times 10 to the third. So if you expand this out, it's going to be 7,000 joules. And we can see that the used is equal to 7,000. That means that 200 joules is converted into something else. Whatever. So the answer is going to be B. A motor is used to lift a load vertically upwards. The load has weight W. The motor produces useful power output P. The load is lifted at a constant velocity V. Which expression gives the time taken for the motor to lift the load vertically upwards through a distance of D? Okay. So we know that power is equal to F times V. Or in this case, P is also equal to work divided by time. So these are the two formulas you should know, just in case, because in different circumstances you're going to use different formulas, of course. So we know that work is equal to force times distance. So we can substitute into here. We get P is equal to force times the distance. We're going to call it D in this case because that's what the question is asking. It's in D rather than S. So, and then we get T. Our force in this case is also denoted as W for weight, which is given here. And then thus we get, and then we want to solve for T. And thus we get T is equal to W times D over P, which in this case is going to be C. Researchers have developed a new type of filament lamp with an efficiency of 40%. Old type filament lamps have an efficiency of 5.0%. The two types of lamps produce the same useful output power. What is the ratio of input power to the new type and the input power to the old type of lamp? So let's call the first one X and the second one Y. So given by this sentence, the two lamps provide the same amount of useful output. So for the new lamp, right, we're given that it has efficiency of 40%. So that means 0.4 times the input power is equal to the efficiency of the second one, right? So 0.05 of the input power, y. And now we have to solve for x over y. And then we just swap stuff around. So you get x over y is equal to 0.05 over 0.4. And this turns out this is equal to 1 over 8, which is equal to 1.25, which is equal to 1.3, which is going to be A. So that's going to be the end of part 2. Thank you for tuning in. If you like this, like and subscribe. Yes, very good. Comment down what you want me to do next. I'm currently in the process of doing review units for 1, 2, 3, 4, and 6. Not 5 yet, but I figured people need this more than the review of earlier units.